Previously, I've derived this expression for the period of a simple harmonic motion. I'm now going to use this to find to see how we can find the periods when we have, say, a spring, simple harmonic motion of a spring, and when we have a pendulum. So let me start by looking at the spring. Now, in the case of the spring, what we need is to be able to find the period in terms of what we know about the spring and maybe the ball. So in this case, we have to think of, for example, say the ball. We might want to know the mass of the ball, because perhaps if you have a more massive ball, it will move more slowly, so it will take longer for one cycle. And if I have a spring that is stiffer, for example, it would exert more force. It would give more restoring force when I pull at it. Okay, so that might cause the ball to move up and down more quickly, and therefore give me a shorter period. So these are the things that will affect that could affect the period. And so what I've written on the mass. So let's say we know the mass of the ball, and we probably need to know the spring constant as well. Now we know from Hooke's law. That the spring constant is related to the displacement by a formula like that, where K is a constant of proportion. It is also called, it goes by a few different names. In this case, I just call it a spring constant. So for a spring, it is something that we can either just measure quite easily, just hang a weight there, calculate, work out the weight and measure the extension, and then just calculate K. So it's something that we can obtain quite easily, measure quite easily on a spring. So suppose that we know, we know the K of the spring, or we have found it. Now what I like to do is to be able, given these numbers, to be able to predict, to calculate the period of the motion. Of course, I can also measure it. I can just pull it, let go, and take a stopwatch and measure it. But it would be nice if I can also calculate. I can also predict from these quantities, and we can actually using let me write down that formula that I got just now again. Using this formula, that T is equal to 2 pi over omega. So what this means is that I must first try and find an expression for omega. Now omega is down here, and the way to find an expression for omega is to find the connection between this Hooke's law and this expression. Now if you look at the two, I have x and x here in common. Okay, that's good. And if I look at F and A, we know how F and A are related. They are related by Newton's second law. So F is equal to ma, equal to kx. Now when I write down this expression, I understand from the use of this minus sign that I have to think about the directions of A, acceleration and displacement. So in order to write down this equation, if you like, more precisely, I should also think about the directions of x and a. And in this particular example, I know that if say the displacement is upwards, say the spring would exert a force downwards, giving an acceleration downwards, because that's a restoring force. So therefore, I understand that I should have a minus sign here. Okay, that was also the same reasoning that gave the minus sign in the simple harmonic equation. Okay, so coming back to this, what I want to do is to find an expression for omega, hopefully in terms of k and m. Now I'm almost there actually. You see I have an a there now. So let me make a the subject. I'll move m over to the other side. So I get this. Now if I now compare this, you see that they are quite similar except that instead of omega squared, I have k over m here. And the way to do it now is to say that k over m corresponds to or is the omega squared. Okay, because the omega squared is just a symbol that is used in this equation. And when I first wrote this down a few sessions ago, I did not actually say what omega squared means, but in the last one or two sessions, I've explained that how omega can be related to circular motion. Okay, but that's from the point of view of trying to solve this equation physically. But from the point of view of looking at a specific example, we need to use Newton's second law and the relation between the force and the x to arrange an equation for a, all right, to find an expression for a in terms of x. So depending on the specific example, like in this case for the spring, I've just obtained this expression, and the idea in this case about the omega squared is that it's just a constant, all right, and that constant corresponds to whatever I get in this place for a particular example. So in this case, since I get k over m in the place of the omega squared, so therefore k over m just corresponds to omega squared. And therefore I can write this down, that omega squared is equal to k over m. And I need omega there, so let me take the square root of this. So omega is equal to square root of k over m. And therefore, t, since this is 2 pi over omega, so that will be inverted. I get m over k. And that gives me the period for the spring. Now, and you can see that the reasoning I used earlier on to think about what quantities in this spring and mass example would affect the period, right? The reasoning is actually it actually shows up here again. You see, I have m there and I have k here. So just now I was saying how if I have a bigger mass, the motion will be more sluggish. It would be slower. Then I might expect that it takes more time for one cycle. If you look at this formula, you see that m is on top and k is at the bottom. So if m is bigger, clearly when I calculate an answer for t will also be bigger. Right? So that agrees with my physical reasoning. And then I said that if the spring is more stiff, if the spring constant is bigger, then it will give a bigger restoring force. It will push more strongly at the mass when it is displaced. And so therefore, we might expect that a stiffer spring, a bigger K, would result in a shorter cycle, right? A faster motion, so a shorter period. And indeed, you can see in this solution that since k is in the denominator of this expression, so when k is bigger, we would calculate a smaller t.